I'm setting out to build the best microcontroller board for robotics. This device has an Arm Cortex-M7 processor clocked at 1 GHz, dual-band Wi-Fi, an inertial measurement unit, and a built-in closed-loop motion controller. Above all else, this board will have first-class support for micro-ROS, allowing seamless integration with the robot operating system. So, what problem are we trying to solve? Robotics is all about coordinating a bunch of motors to perform some task. Take a 3D printer, for example. A 3D printer has at least 3 motors that move the print head in X, Y, and Z. There's also a 4th motor to extrude the filament. Industrial robot arms often have 6 motors. This allows it to articulate a tool not just in position, but also in orientation. No matter which machine you're looking at, the fundamental challenge is always writing software that coordinates a bunch of motors. Now, I'm an embedded systems engineer, and I've worked on many projects trying to solve this problem. What I've realized is that each of these projects has the exact same set of challenges. Real-time signal processing, which means coordinating motors by tightly synchronizing their electrical signals. Closed-loop control, which means using feedback to make sure the motor goes exactly where you need it to. Interpolation, which means generating a smooth trajectory between points while bounding the velocity and acceleration. And fault handling, which means monitoring the system's state and ensuring that faults lead to predictable actions. As common as these challenges are, none of them are trivial. For example, real-time signal processing requires precise, low-jitter electrical signals. This often involves using a microcontroller's hardware timers or offloading to dedicated hardware like an FPGA. Poorly designed systems can lead to high quantization error and loss of position accuracy over time. Closed-loop control adds many nuances. You might be familiar with the famous PID controller. It calculates the error between the motor's set point and measured position, then applies 3 corrective terms to compensate for that error. While this might sound simple enough, textbook PID controllers fall short in real-world applications. Mechanical saturation can lead to integrator windup, the derivative term amplifies high-frequency noise, and using PID without some feed-forward term introduces phase delay. In practice, real-world motion controllers are much more nuanced. Interpolation is challenging if you're not familiar with existing methods. The most common method is trapezoidal interpolation, which means starting from a piecewise acceleration profile and integrating to find velocity and position. While this is conceptually simple, real-world systems have to optimize the trajectory for multi-axis spaces and handle edge cases such as short moves that never reach their cruising speed. Fault handling is commonly one of the last things considered when teams architect their motion control systems. Poor fault handling plagues designs with reliability issues, makes faults hard to recover from, and can lead to mechanical damage. In a vacuum, none of these issues are particularly hard to solve, however, they add up very fast, and these issues must be solved every single time a new motion controller is deployed. This engineering overhead is unacceptable. My proposal is a single, low-cost integrated circuit that abstracts away all of this complexity. A user simply sends high-level commands, and the IC handles the rest. That's what I'm working on right now. Assuming no setbacks, this chip will be available by the end of the year. This series is about building a high-end development board that uses this IC. My goal is to create a device that is just as easy to use as an Arduino or the famous Teensy, but with higher performance and extra features that make it great for robotics. Let's get started. The first thing to do is choose the core components. For the main microcontroller, I went with this blazing fast option from NXP. Currently, the Teensy 4 is the gold standard for high-speed dev boards, sporting a 600 MHz Arm Cortex-M7 processor. The G2 Nano will sport an M7 processor clocked at 1 GHz. That's 67% faster. I chose this processor because, to my knowledge, it is the fastest M-series core on the market. The Wi-Fi module was actually pretty tricky to source. Many existing development boards only support single-band 2.4 GHz Wi-Fi, and this is a huge pet peeve of mine. If I'm going to add Wi-Fi, I'm going to add support for the 5 GHz band as well. I landed on the U-Blox Maya W1 because it supports dual-band Wi-Fi, Bluetooth, and has an integrated antenna. It's also based on a chipset that has a reference design for the real-time operating system I plan to use. I also want there to be a way for the G2 Nano to understand its own motion. A very effective way to achieve this is to combine an accelerometer, a gyroscope, and a magnetometer. The accelerometer measures acceleration, the gyroscope measures relative orientation, and the magnetometer measures magnetic fields, like a compass. I selected 2 chips for this. This one contains the accelerometer and gyroscope, and this one contains the magnetometer. The next question is, How do you program it? That, and once it's programmed, how do you debug it? Print statements are great, but more complicated programs benefit from hardware debugging. That is, the ability to use tools like GDB to set breakpoints and step through the code on the hardware itself. Ideally, you should be able to do this without an expensive external debugger. I decided that instead of programming the microcontroller directly, I'm going to use a smaller microcontroller running firmware called DAPLink. The smaller microcontroller will talk to a host PC over USB and program/debug the main microcontroller. Additionally, it can act as a UART bridge, allowing printf and scanf to work over USB. The next step is to draw up a schematic. I'm using KiCad for this because it's free and easy to track with Git. This is great for an open source project like this. I've broken the schematic into 3 pages: User I/O, Configuration, and Power. The User I/O page is meant to show pretty much every connection that the user should care about. It shows which pins go to the Wi-Fi module, the IMU, the magnetometer, and the real-time motion control IC. It also shows how the button, LED, and GPIO are connected. The Configuration page is meant to show anything responsible for configuring the main processor, including the external flash memory, any strapping pins, and the hardware debugger. Finally, there's the Power page. There's not too much excitement here, it just shows how the main processor is powered and where most of the voltage rails come from. Layout is where the fun begins. Here, we have to decide the board's form factor, lay out the components, and draw tiny traces that connect each of the pins together. I decided to keep the board as small as possible. It's 0.8 by 3 inches, which is roughly the size of a stick of gum. I chose this form factor because I know that I always reach for a board like this. They fit nice on a breadboard and they don't take up much space on your desk. They also make it trivial to design a landing board to tie them in with the rest of your system. The point is, they're great, and they're the easiest to use across all stages of development. For the stack up, I went with a 6-layer board that has 3 signal layers, 2 ground planes, and a power plane. Since this board is so dense, I probably could have sacrificed that second ground plane for an extra signal layer. Doing so would have saved me some extra work, but 3 signal layers ended up being fine. And with that, we're done. This board turned out beautiful. All that's left is to send it out for fabrication and wait for the prototypes to arrive. Once those boards get in, we'll start diving into the firmware side of this project. My hope is to start by simply blinking an LED, then to get the Zephyr RTOS running. From there, we've got a lot of work ahead of us. I have to write drivers for each peripheral, port micro-ROS, write documentation, create user guides, and so on. I'd also like to get MicroPython running. The processor is so fast that you shouldn't even notice the overhead from the Python interpreter. I see MicroPython being super useful for prototyping on this board, especially when your firmware needs to do something complicated like connect to Wi-Fi. Anyway, I'm getting ahead of myself. Everything we've done so far is on GitHub. The board is beautiful, blazing fast, chock full of features, and it's the size of a stick of gum. The prototypes should be here before long, so stay tuned.